We've all thought about rewinding time, whether to fix that cringeworthy mistake or a sneak peek at next week's sports scores. But let's be real, those thoughts fade. For most of us, time travel is just a fun movie idea. But for astrophysicists, time travel isn't just sci-fi. It's a serious puzzle hidden in the fabric of space-time. And now, new models suggest the universe might just allow time to bend in ways that didn't seem possible. Humans were intrigued with manipulating time long before complex scientific models. In an ancient Hindu story, a king visits the heavens for minutes and returns centuries later. In a Japanese legend, a fisherman spends days in an underwater palace and comes back to find generations have passed. These are some of the myths that hint that time doesn't flow the same everywhere. And time traveling as a concept didn't just pop up from regret or curiosity, it also came from watching space. Time feels like one constant in our lives. It's always moving forward like a river. It flows forward and it's predictable. But when we zoom out, way outside of our planet, it's a different story. To physicists, time bends, stretches, and slows down depending on how fast you move or how strong the pull of gravity is. And that's not just a theory, it's measurable, proven, and built into the technology we use every day. For example, astronauts on the ISS orbit Earth at 17,000 miles per hour. And their clocks tick just a tiny bit more slowly than ours. It's only milliseconds, but technically, they've aged less. You can see this effect in your everyday GPS as well. Satellites up there feel less gravity, so their clocks tick a bit faster. Imagine playing a racing game where your car and your controller are a bit out of sync. That's why GPS needs constant tweaks, or else your phone would think you are miles away. Gravity also messes with time. Scientists proved it using 2 atomic clocks. Atomic clocks are like the ultimate devices that measure time. They don't tick with gears or crystals, they tick with atoms, the universe's own metronomes. One clock was on a skyscraper roof, the other closer to the ground. The lower one, feeling stronger gravity, ticked just a tad more slowly. The difference was tiny, but it proved that even height can tweak time. Now picture being near a black hole where minutes could equal years elsewhere. This might help you get those mind-bending scenes from Interstellar. So yes, time bends, and scientists know this. And the challenge now is learning how to do it on purpose. Einstein's work proved that time could move differently for different observers. The faster you move, the more slowly time passes for you. This phenomenon is called time dilation. Think of Marvel's comic Flash. He runs incredibly fast, but he doesn't really slow the world down. His own clock runs more slowly, so to him, everything else looks frozen. If you could reach the speed of light, your time would almost stop entirely, while the rest of the universe would keep racing ahead. For decades, physicists believed that was the only path to real time travel. But the Flash is a superhero, and Einstein proved that nothing with mass could reach that speed. The faster you go, the heavier you become, and the more energy it takes to keep accelerating. To actually reach light speed, you'd need infinite energy, because your mass would become infinite too. Since infinite energy doesn't exist in the universe, it's physically impossible. That's why physicists started asking questions like, if time can stretch and bend, could it also fold? In 1994, physicist Miguel Alcubierre posed a question. Could Einstein's math let us travel faster than light, not by breaking the rules, but by bending space itself? His answer was, maybe. He imagined a warp bubble, a region of space surrounding the ship that moves with it, carrying it along like a cosmic conveyor belt. In this bubble, the spaceship itself doesn't move. The space in front shrinks, the space behind stretches, and the ship rides the wave forward like a surfer gliding on a moving sea. Inside the bubble, the ship feels no motion. It's sitting still, but the bubble carries it across huge distances. And because the ship isn't moving through space faster than light, it doesn't break Einstein's rules. The universe itself does the moving. That hypothetical bubble would need a special kind of energy to bend space-time this way. Originally, Alcubierre's equations required negative energy or exotic matter, a substance that's never been found in usable amounts. Early estimates said we'd need more energy than Jupiter could provide. For years, scientists have wondered if the universe could allow something like a cosmic shortcut without breaking the known rules of physics. While nothing practical has been found yet, theorists have explored models that closed time-like curves, loops in spacetime that bend back on themselves. Here's how it works. Imagine spacetime as a giant sheet. Normally, moving across it takes time, like walking across a field. But a closed time-like curve is like drawing a circle on that sheet. If you walk along it, you could eventually end up back where you started. In spacetime terms, the start and end could be different moments in time. So instead of just moving through space, you're following a path that loops through time, a theoretical shortcut to the past. This isn't pressing a button to hang out with your younger self, it's more like a time detour, a loop in the universe that could let something trace its way back to the past, all without breaking the speed of light. Einstein's math already lets spacetime do gymnastics near spinning black holes, twisting like a cosmic corkscrew. Physicists can explore these loops on paper, but creating one in a lab is far beyond our reach. If one day we could turn this math into a real spaceship, a warp bubble wouldn't actually make the ship go faster than light. Well, technically, there would be no speed. Inside the bubble, the ship wouldn't move at all. Instead, it would fold space like a piece of paper, bringing two faraway points together. The ship could get there in minutes while still obeying the cosmic rules. This is how it worked in the famous Star Trek series, and what many movies adopted as a method for space travel. In a hypothetical situation, a warp bubble wouldn't just be for spaceships. You could send a probe, a package, or even a cup of coffee across the galaxy without it actually moving through space. It's pretty cool, because since the bubbles move space around it, everything inside stays totally still relative to the bubble, which means no spills and no weird forces acting on the coffee. However, we are still far away from that point. The challenges we face are pretty massive. We still don't have enough energy, and folding space-time at will is still out of our reach. But for the first time, the math suggests that it's not impossible. What used to seem like pure sci-fi is now popping up in real science journals. These concepts aren't just about whipping up time machines or warp drives. Even if we never pull off a warp drive, figuring out how space-time works is a big deal for understanding reality. For now, it's all theory and simulations, but every experiment pushes the impossible line a little further. Yesterday it was no, today it's maybe. And in science, maybe is where the most exciting things happen. So while we're not ready to build time machines or bubbles across galaxies yet, scientists can now study and test these ideas using real physics, which will lead to new exciting discoveries. That is, unless future Earthlings figure out how to do it maybe 1,000 years from now, so they travel back in time to show us how we can do it ourselves. Which will create a grandfather paradox, unless someone sends the idea back in time and creates a closed time loop. Scott Kelly is a lot of things. An American engineer, a retired astronaut, and a time traveler. Wait, what? Kelly commanded the International Space Station on several missions. On one of those trips, he spent 340 days aboard the giant, floating science lab orbiting Earth. While he was up there, improving the water recycling system, testing heat transfer in microgravity, and doing all the other genius-level stuff astronauts do, he was also aging. But not like you, me, or even his identical twin brother Mark. He was actually aging slower than all of us. Okay, so Both brothers are astronauts and have been to the International Space Station, but Scott spent way more time up there. About 10 times as long, actually. And here's where things get more interesting. Even though Mark was born 6 minutes before Scott, he is now 6 minutes and 5 milliseconds older. That happened because Scott aged a little more slowly while he was orbiting the Earth. And astronauts age slower because they're moving much faster than us, at 17,500 miles per hour. Basically, the faster you go, the more time stretches out. So the closer you get to traveling at the speed of light, the slower you age. From Scott Kelly's perspective, nothing felt unusual up there. Time passed like normal for him. But he actually aged less than his twin brother over the same period of Earth time. So when he returned, we can say that he had essentially leapt forward in time relative to us. So, if traveling close to the speed of light lets us leap forward in time, that means astronauts have already kind of achieved time travel. Sure, it's a bit of a letdown that it doesn't happen like Back to the Future, you know, hopping into a cool futuristic car and zipping into another timeline. But this is real, at least according to some scientists. Real time travel isn't about jumping from one moment in time to another, like going back to the age of the dinosaurs, then hitting a button to fast forward to the year 2100. The time travel that's possible today is more about actually living into the future. It's about moving faster than 1 second per second, just like Scott Kelly did. To explain the theory behind this wild idea, we have to bring a celebrity into the conversation: Albert Einstein. Think about your childhood and your retirement. Whether it's in your past or your future, time always ticks at the same steady rate. But then along comes Einstein saying, sure, but it's not that simple. He introduced the idea that time is relative. In other words, the amount of time you experience compared to someone else depends on what you're both doing. And where exactly you are in the universe. Time is not the same for everyone. Here's an example. You're sitting on a bench, holding a melting ice cream cone. Meanwhile, your friend zooms past in a super fast spaceship. For you, maybe the ice cream melts in 5 minutes, but for your friend flying at a crazy speed, this same scene took less time on his watch. That's time dilation. Time actually moves slower for things that are moving faster. That's the heart of what's known as special relativity. We actually proved Einstein's theory back in the 70s. 2 scientists took super accurate atomic clocks and flew them around the world on planes, first going east, then west. They compared those clocks to a third one that stayed on the ground. When all 3 were brought back together, they showed different times. The clock that flew east in the direction of Earth's rotation lost 59 nanoseconds, and it was moving faster relative to the ground. The one that flew west against Earth's rotation was moving slower, so it gained 237 nanoseconds. Now, think about those astronauts living in space moving way faster than we are. They travel at about 5 miles per second, orbiting Earth roughly every 90 minutes. If you do the math, spending 1,000 days up there lets you skip about 0.027 seconds into the future. I know that doesn't sound like much, but that's because the speed of the ISS is tiny compared to the speed of light. Still, if we keep going with that idea, it pretty much makes the astronaut Oleg Kononenko humanity's greatest time traveler. In 2024, he set the world record for the most time spent in space: 878 days in orbit. Okay, so we now know that Kelly and Kononenko are, in a way, living in the future. But what about traveling backward in time? Well, I'm sorry to say, traveling back to your glorious high school days is a whole lot trickier. In theory, we could, but in practice, it's pretty much impossible. Imagine space and time as this big, stretchy fabric, and gravity is what bends it. Kind of like when you put a heavy bowling ball on a trampoline. In theory, if you could bend it just right, you might create a shortcut through space and time called a wormhole, a tunnel that connects two different points. Let's say the present and the past. Now, usually, gravity pulls things inward. It wants to collapse tunnels, not keep them open. So the walls of this tunnel are constantly under pressure from the universe, trying to squish them shut. To stop that from happening, and to keep the tunnel open long enough for something or someone to go through and get to the past, you'd need something that pushes outward, against the collapse. And that's where negative mass comes in. Negative mass is a weird, theoretical idea in physics. Unlike regular mass, which pulls things together with gravity, negative mass would actually repel things. It would push away instead of pulling in. It's like using anti-gravity to keep the tunnel from closing. It would act like braces, holding the tunnel open from the inside. But here's the problem. We have never actually seen negative mass. It's just something that might exist on paper, in math, but no one's ever found any in real life. Plus, there's something called the self-consistency principle. Basically, it says that time travelers can't create time paradoxes, like those crazy scenarios in the Butterfly Effect movie. Let's say you go back in time to stop your granddad from meeting your grandmother. But here's the problem. If they never met, that means your parents were never born. And if they weren't born, well, how do you exist? That's a time paradox. Something that causes all sorts of inconsistencies in the universe, making everything a total mess. And according to the self-consistency principle, that's impossible. It just can't happen. Some specialists, though, think they have an answer to the grandfather paradox. All we need to do is think about time as an endless loop with no starting point. In a closed time-like curve, as this theory is called, the past and present blend together in an eternal time loop. There's no way out. There's no changing things. It would all look the same if played in reverse. For example, what did you do yesterday? Let's say you woke up, brushed your teeth, worked all day, had your meals, and then went to bed again. Following the closed timeline curve theory, if you could go back to yesterday, you'd do those exact same things in the same order, no matter how hard you try to take the day off. Because in a closed time-like curve, you're attracting not just your steps, but every single second of reality itself. And that's the only way time travel could be possible. So, even if we somehow manage to build a time machine, and even if we give it our best shot to change the past, nature will always find a way to prevent contradictions. In the end, everything would have to align perfectly to keep our history from becoming a mess.
You may have time traveled multiple times already. You just don't remember it. A recent study says that all your memories of the trip would be completely erased as soon as you're back in the present. And you can blame it on something called entropy. To explain it, we first need to talk about closed time-like curves, or CTC. This is a closed path where a particle could travel, and it ends up right back at its starting point, at the exact same time it left. In other words, it's like a cosmic time loop. Take this notebook paper. Picture each line as a different timeline with a beginning, a middle, and an end. Now, if you roll that sheet of paper, the lines connect. Suddenly, they form a continuous line with no beginning or end. That's what CTCs are. Closed timelines that don't have a starting point. Past and present blend together in an eternal time loop. Now, a more practical example. You're taking a walk around a park. A woman jogs past you, and a dog starts barking. You keep walking, but then, wait a minute. You realize you're back at the exact spot where you started. The same woman jogs by, and the dog barks again. But here's the thing. It's not just that you've returned to the physical starting point of your walk. In a closed time-like curve, You're retracing not only your steps, but every single second of reality itself. Alright, now think about the big moments in your life: being born, graduating from college, getting married. If all these events are part of one big time loop, that means time travel is possible. It sounds crazy, but there's a concept behind it called the self-consistency principle. It says that time travelers can't create time paradoxes. I mean, time travel can't just be this wild, chaotic mess like those crazy butterfly effect scenarios. Even if you go back in time, everything in your life still has to fit together in a way that makes sense and lines up with what we already know today. I'll explain. Let's say you go back in time and stop your mom from meeting your dad. But here's the problem. If they never meet, then you wouldn't exist. And if you don't exist, how could you have gotten into the time machine in the first place? That's a time paradox. That's why time travel could only work within these closed time-like curves. No matter what you do, the past, present, and future are locked in. They're always going to play out the same way, like a loop. Okay, so now you understand what CTCs are and why they're important for time travel to make sense. Now, we can finally talk about entropy and why it's probably the reason we'd lose our memory after a trip to the past. Entropy is a way to talk about disorder, chaos, or randomness in a system. Imagine a super clean, minimalist bedroom where everything is neatly arranged. Everything's in order. That's low entropy. But then, picture a messy teenager moving in. Every day, clothes, books, and random stuff gets scattered around the room. It's a mess. That's high entropy. In nature, things usually trend toward more disorder unless you actively work to keep them organized. Like this ice cube. It's made up of water molecules, all neatly lined up in perfect order. Low entropy. But if you take this ice cube out of the freezer, it will melt into water. See how the puddle looks messier now? In this form, the water molecules can be arranged in so many different ways. They're all disordered and random. And that's higher entropy. If we apply this idea to time travel within a CTC, the closed time loop, things get even more interesting. According to specialists, a key feature of this circular journey is that the level of entropy has to be the same at both the beginning and the end of the trip. Here's an example. You're just living your everyday life. Nothing too exciting going on, so the entropy level is low. But then, you get inside a time machine and go back to the past, right before you broke up with your high school sweetheart. By traveling through time, the chance of you changing the past and totally throwing your story into chaos is pretty high. Let's say you don't break up with her, and in this second chance, you decide to propose to her. See how everything could go totally sideways, right? So, when you go back to the past, the entropy is at a super high level. Now, you get to the exact moment when you're about to talk to your past love. At that point, entropy is at its peak. You're about to kneel down, show her the engagement ring, when, well, here comes the self-consistency principle, and it throws a cold bucket of water on this whole romantic idea. Remember, in a closed time-like curve, nothing can significantly change the present reality. All the changes a time traveler makes in the past can't cause any historical paradoxes. So, sorry to say, but you're not going to end up with her anyway. You decide to hop back into the time machine and return to the present. You get back into your routine, your job, and well, your single life. After completing the time loop, your timeline is back in order. Now, the level of entropy is low again, just like it was at the beginning of your journey. It's like you did a reset on the system. And that's the bad side effect of all this. Pressing this reset button would probably erase all your memories of the trip by the time you get back to the present time. Unlike in the movies, a time traveler probably won't recall anything. What? Now, answer in the comments. Even if you can't remember what you did after going back to the past, would you still take the risk? I'm guessing your answer would be, yeah, of course. That would be my answer too. After all, we could bring our phones and still make tons of cool photos on this trip, right? Well, no. This is where the laws of physics crush our hopes, again. The second law of thermodynamics says that in an isolated system, entropy, or disorder, tends to increase over time. But this doesn't apply only to humans, but also to non-living things. It's why you can't unscramble an egg, unmix coffee from milk, or take your phone into a time machine. If a time traveler stores any data on their smartphone during their journey, experts believe it will probably get wiped out as soon as the trip ends. All the videos, photos, poof, gone. That's because machines probably wouldn't work properly when we go back in time. For example, let's say you bring a classic analog watch with you. For all the reasons we've already talked about, when you come back to the present, the clock needs to be exactly where it left off. I mean, the clock hands should be in exactly the same position at the beginning and the end of your journey. But to make that happen, it's likely that the frequency and number of ticks during the trip will be different. That could cause small problems in clocks made for regular time, making them unreliable. Something similar could happen with your phone. Its system probably wouldn't work as it should. All these consequences of time travel were described in a study by a mathematician published in 2024. While his theory doesn't determine whether time travel is actually possible, it does point out the strict conditions that would have to be met. And, well, it seems like having a time machine at home might not be as great as it sounds. In the end, you wouldn't remember a single thing about your amazing trip, and you'd probably just end up exactly where you are. Turns out we have some ways to solve the time travel paradoxes. Time travel sounds enticing, but brings with us a lot of problems. Take, for example, the famous grandfather paradox. Imagine that you travel back in time and prevent your grandparents from meeting. This alters the course of history. But how? If you erase their encounter, you cease to exist, so you couldn't even travel back in time to alter the past in the first place. There's also the bootstrap paradox. Let's say we travel back in time and give Beethoven his own compositions before he ever penned them. He gets famous for the very music you provided. But where did it originate? Did you start it? Or was it Beethoven who started it? There are many theories about time travel. One of them involves alternate timelines and parallel universes, like in Back to the Future, for example. If parallel worlds exist, we could hypothetically travel in one where the events unfolded differently, while our original timeline stays the same. This is a beautiful and paradox-free approach, but this is pure sci-fi, as we have no concrete evidence of parallel universes. So what scientists are trying to do instead is to figure out whether time travel is impossible in this one universal timeline. We've been exploring this equation for over a decade and created a fascinating concept called a closed time-like curve, or CTC. Imagine taking a path that forms a loop, bringing it back to where it started, but in time. We know that space-time is like a wobbly piece of cloth which can curve and bend when we place heavy objects on it. In some situations, like near massive objects such as stars or black holes, space-time can be curved. Now imagine an object that's so heavy, with gravity curving the space-time so strongly that it literally loops on itself. If this idea turns out to be real, it could suggest the possibility of traveling back in time in our world line. This possibility is fascinating, but it also creates tons of problems, and scientists may have found the ways to solve them. One of the solutions is that doing paradoxical things can be simply impossible. In this scenario, we assume that the universe has some mechanisms of self-consistency. It means that while you can still travel in time, you're restricted in the actions you can take. For example, you may not be able to go back and alter your family's history, but there's nothing inherently illogical about traveling back in time to simply interact with your ancestors. In this scenario, the universe only forbids you to do logically impossible things. Scientists decided to conduct an experiment to check if it works, and the results were pretty terrifying. The experiment conducted involved the creation of a theoretical time machine. This is also called an in-principle time machine. This wasn't a physical device, but rather a quantum simulation. In the simulation, they attempted to send a photon back in time by a fraction of a second and make it interact with its past self. The goal was to find out what the photon will do. Will it destroy its previous self, avoid the interaction, or something else? What happened is that as the photon approached its past self and was getting closer to the point of creating a paradox, the experiment tended to fail more frequently. In other words, it seems like the laws of physics or the fabric of the universe might have some weird built-in mechanisms that prevent time travel paradoxes. In that case, the question is, how does the universe understand what is logically impossible? And how does it prevent us from doing these things? Which is quite scary to think about. There's another theory that the universe allows paradoxical things to happen, but also self-corrects them. Imagine a time traveler going back to stop some health condition from spreading. According to this theory, even if the traveler succeeds, this health condition would find another way to spread, avoiding the paradox. Or maybe we all exist in time loops. These loops allow objects to interact with their past selves while still maintaining a consistent timeline, because there's no beginning point. For example, trying to prevent a historical event could result in accidentally catalyzing the event we were trying to prevent. This idea challenges our understanding of classical physics and free will. But all these ideas are purely theoretical, and to test them, we first need to find the mechanism to actually travel back in time. Talking about practical time travel, we mentioned that space-time curves around very heavy objects. Does it mean that black holes can be portals to the past and the future? Maybe. Black holes are formed when a massive star collapses inward. Their gravitational pull is so intense that even light can't escape. This means they're perfect for bending not just space, but even time itself. You might remember this from Interstellar. Near a black hole, time slows down. This effect is so pronounced that a year near a black hole could translate to decades on Earth. In that case, traveling back to the past using a black hole is theoretically possible. If their gravity twists time so much that it wraps back on itself, creating a closed time-like curve, and you could enter this loop, you'd find yourself on a journey from the future to the past. But there are some problems with this. First, you can only travel into the black hole's past. Second, to enter the loop, you'd likely have to cross the event horizon, the point of no return around a black hole. To escape one, you'd have to travel faster than light, which is currently impossible. So, while black holes might hold the keys to time travel, the journey inside one might be your last. But not everyone agrees that closed time-like curves exist at all. Recent research has shed new light on this topic. The results showed that time can only move forward. The research offered a fresh perspective on how light behaves when it encounters different materials. When light moves through empty space, it travels at a constant speed of 186,000 miles per second. But when it encounters substances like water or glass, its speed can change, causing it to bend or refract. While scientists have equations to describe this behavior, they struggled with the problem of the change of the speed of light at the boundary in different mediums. Well, researchers proposed a solution to this puzzle by reconsidering how light moves through time and space. They figured out that it always remains constant as it travels through different mediums. No matter what the light encounters, it always moves forward in time. This means that light and other waves like it follow the same one-way path through time that we do. Another thing is that light also always saves its momentum, and it always stays the same, pointing forward in time. And finally, even with general relativity and with gravity bending light very strongly, it still keeps pointing forward. It can slow down to the point of feeling like time stopped, but never move backwards. This challenges our previous notions about the relationship between light and time. It implies that time has a definite direction for all waves, making it impossible to reverse. However, their equations have only been tested in one dimension, and experiments are needed to confirm if this theory holds true in reality. Stephen Hawking also disagreed with the idea of traveling back in time. He proposed a theory called the chronology protection conjecture. This idea says that the laws of physics stop time travel on large scales, even when theories like general relativity say it's possible, and that closed time-like curves simply can't exist. Hawking said that traveling back in time would mean creating new matter, which goes against the laws of physics. Although we're far from building actual time machines, if we keep diving into mathematics, we might find the truth one day.
You of course know that the Earth is bathed in sunlight every day. Every day we flicker different light sources on and off, mechanically, without even thinking about it. But imagine that one day you casually flicker the lights off, fall asleep, and wake up in a completely different era. Let's see how it happened and what it has to do with light. Quantum physics is quite crazy. Classical physics is like a movie projected from start to finish, while the quantum world is like having an ability to take the remote control and manipulate scenes you're watching. Fascinating and mysterious. Let's say you have a regular light switch that can be either on or off. That's like a regular bit in computers, which can be in one of two states, 0 or 1. But in quantum computers, there's a special kind of switch, a switch called a qubit. Unlike the regular bits, a qubit can exist in multiple states at the same time. It can be both 0, 1, and all things in between, like having lights on and off simultaneously. Yeah, our universe has some weird rules. This mysterious property, called superposition, allowed us to do something incredible recently, to reverse time back. At least in a tiny experiment with quantum computers. It's the autumn of 2022. Two groups of scientists, one from Oxford and the other from Vienna, decided to conduct a weird experiment. They played around with a quantum computer to create a program that reverses time. They took a tiny electron and tried to make it go backward for a time for just a fraction of a second. It would be like breaking a billiard ball triangle, where the balls go from order to chaos and then magically reverse. But don't get too excited about time travel yet. Unfortunately, we're not sure if it's possible to recreate it in real life. The scientists cracked some numbers and found out that if we observe 10 billion localized electrons every second for the entire age of the universe, we'd only see something like this happen once. And it would only take the electron back a tiny fraction of a second. So they didn't invent a time machine. They just managed to create this simulation in quantum computers. There's another catch too. The larger the simulation, the more complex and less accurate it becomes. In our experiment, we only used one qubit, and we managed to reverse time. In a 2-qubit setup, scientists could reverse time only in 85% of cases. And in a 3-qubit setup, it dropped to 50% with more errors. If we keep adding more qubits, we won't be able to pull this off at all. Plus, the success depends on the amount of information the system can store. For example, teleporting a person would be almost impossible because humans have so much information inside them. So, unfortunately, no time machine so far. But there are some possible uses of this discovery. Reversing qubit states in a quantum computer can help correct errors during development, sort of like a little Control-Z in real life. So, it was a tiny step to more exciting discoveries in the future. For example, recently they demonstrated another crazy little thing: send light itself back in time. Now, light isn't mere luminary. It has superpowers that we can't even imagine. The ancient Greeks believed that our eyes emitted visionary beams. Sir Isaac Newton proved them wrong hundreds of years later when he conducted his experiments with prisms. The prism broke the pure white light into a beautiful palette, and that's how we found out that light actually consists of tons of different colors. Many years later, scientists learned even more, that light is a wave. And even later, in the 20th century, we discovered the final paradox, that it's both a wave and a particle, a dual existence in one photon. And the more we learn about light, the more crazy things we find. In 2016, scientists managed to freeze the light in time. They put photons, the tiniest light particles, in ultra-cold atomic clouds. Then they managed to stop it, again, for just a moment. But the fact that it's even possible is already incredible. Then scientists got even bolder. They decided to try not only to freeze the light, but to move its direction in time. They took a special crystal and passed a photon through it, thus initiating the so-called quantum time reversal. As a result, the photon started moving into both the future and past at the same time. The science magic behind this involves two quantum principles: superposition and quantum symmetry. We already mentioned the first one. It allows tiny particles to exist in multiple states at once. Now, the second principle says that even if you flip particles around like a mirror, they'll still follow the same laws. Combining this, scientists crafted a photon that defied the usual forward march of time. But again, it's nothing super fancy yet. This time flip only works for specific particles, not entire humans. And even if it did work for us, rewinding a person even for a second would take a super long time and a lot of energy. But the fact that we can change the light's speed and make it change directions is already amazing. And scientists already see some possible applications to this. For example, Harvard researchers suggest a cool way for spacecraft to zip through space at the speed of light by hitching a ride on supernovas. Usually, traveling to other stars takes an insane amount of energy, but these scientists have a wild idea. They think that spaceships could use natural events like hypervelocity stars and meteors zooming from supernovas to reach super-fast speeds. It's kind of similar to how sailing ships catch the wind. Advanced civilizations could use these energy bursts to speed up their spacecraft. Imagine a cool spacecraft with solar or magnetic sails harnessing the power of a supernova boom. These sails could use the pressure of the sun's radiation to work, so that we wouldn't need any traditional engines or fuel. Plus, these sails concepts are much lighter and cheaper to launch into space compared to regular spacecraft. The team is already working on a light sail accelerated by lasers to reach 20% of the speed of light. It might not sound like a lot, but it's actually an insane speed. Their dream is to help humanity make a swift journey to Alpha Centauri in just 2 decades. Isn't it amazing how many things we can do with light, and not just in our imagination? Let's go to more practical achievements. Recently, a Canadian camouflage company called Hyperstealth Biotechnology Corporation has crafted an actual invisibility cloak. The wizardly cloak doesn't need any power source, is as thin as paper, and won't break the bank. Hyperstealth envisions a world where this material can cloak people, vehicles, ships, spacecraft, and even entire buildings. It's still in a prototype phase, but it already works pretty well. They name this incredible technology quantum stealth. It bends light in a way that can make objects disappear from sight. It can render objects nearly invisible, not only in the visible spectrum, but also in ultraviolet, infrared, shortwave infrared, and it even throws in thermal spectrum blocking for good measure. The technology works thanks to the lenticular lens, a corrugated sheet with outward curving lenses. When stacked in a specific way, these lenses refract light at various angles, creating spots that block light and conceal the object behind the material. Unfortunately, it doesn't give you a full invisibility effect, but maybe someday we'll achieve it, if we keep working on it. If you hide behind it, it will look like a little dirty or blurred glass, but you won't be visible. If you put this veil in front of your body, you'll look like a floating head. Scientific progress is in full swing. Maybe one day we'll be able to reverse time not only for little light particles, but for entire humans. Until then, let's enjoy our invisibility cloaks and stay curious. Okay, so you've seen the movies and read the books on time travel. Most of them tell stories about entering some futuristic boxes, and in the blink of an eye, you're in some different epoch. For now, this is just sci-fi. But there are ways to make time travel possible, at least theoretically. We just don't have the technology figured out yet. For starters, time travel to the future could be achieved by traveling at high speeds, but not just getting a ticket on the superhighway kind of speed. This is based on Einstein's theory of special relativity. It explains that time slows down for objects that move at really high speeds. And the good news is scientists have already tested this theory, and it looks promising. They did it with the help of two identical clocks. One was placed on a jet, and one stayed on the ground. They found that the clock on the jet ticked slower than the one on the ground because of how fast the jet was moving. The faster an object is moving, the more time will slow down for it. Currently, the fastest speeds achieved by human technology are seen in a special type of particles called neutrinos. Some of these can move at almost the speed of light. At these speeds, 1 second for the protons is equal to 11 months for us. Now, we might be able to time travel to the future with the use of gravity, too. This idea is based on Einstein's findings, namely his theory of general relativity. Now, this theory explains that the stronger gravity is, the more slowly time moves. This means that as you get closer to the center of the Earth, the strength of gravity increases. And if you think about it like that, time actually passes more slowly for your feet than for your head. Now, is that why I'm always late for stuff? Good excuse. This effect has been measured too, with the help of the same strategy with two identical clocks. Scientists placed them on shelves at different heights and measured the rate of ticking. The clock on the lower shelf ticked more slowly because it experienced a slightly stronger gravity. But this option comes with a catch. To be able to travel to the far future, you'll need to find a place with extremely strong gravity, like a black hole. That's a point in space where the gravity has so much force that even light cannot escape it. There, gravity becomes so intense that matter gets squeezed into a tiny space. The closer you get to the black hole, the more slowly time moves. However, traveling via a black hole is very dangerous, mostly because it's a one-way ticket. Once you cross its edges, there's no coming back. Now, here's a fun fact. The GPS systems we use on our phones and in our cars already have to account for time dilation effects in order to work properly. That's because of the speed of the satellites they use and the gravity they feel here on Earth. Without these corrections, your phone's GPS wouldn't be able to pinpoint your location on Earth very precisely. Meanwhile, the third option has less to do with the universe's unknown forces and more to do with our own bodies. Scientists are trying to find ways to time travel to the future by slowing down the body's own processes. It's not time travel per se. You wouldn't technically be going anywhere. But if your body stays put for a long period of time, you could eventually wake up in the future. Some animals, like bears and squirrels, can slow down their metabolism during hibernation, which means they don't need as much food and oxygen to survive. Specialists are trying to figure out if humans can do the same thing. They're working on ways to make people go into a short-term hibernation for a few hours to begin with. This could be helpful for medical emergencies too, in order to help a person before they can safely get to the hospital. In 2005, scientists were able to slow down the metabolism of mice by exposing them to a small amount of special gas. However, when they tried to do the same thing with larger animals, it did not work as effectively. Our fourth option of traveling through time is really unique. It involves a special type of shortcuts that may exist in our universe called wormholes. Now, before we move on, let's try to understand what they are. You'll need to picture two balls and a trampoline. If there's no pressure applied on the trampoline, it stays flat. Now imagine the two balls placed on the trampoline symmetrically. If you look at them from this perspective, there's no possibility of them ever touching. But if you put enough pressure on the trampoline between the two balls, this flexible fabric can stretch so much that the two objects might potentially touch each other. The same thing happens with stars in different star systems. They're big enough to curve space around them. That's why most planets tend to orbit around a star. The tunnel between those 2 points would be a wormhole. These wormholes could be used to travel long distances, like 1 billion light-years, or even visit different times. Now, many scientists, like Stephen Hawking, think that wormholes might appear and disappear, but be very small, smaller than atoms. The problem is that we don't know how to catch one and make it bigger so that people can use it. This would take a lot of energy, and we don't know if it's even possible. Some astronomers say that even if we could find a wormhole and enter it, it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole slamming shut, like a rubber band that's been stretched too much. Now, the fifth solution for time traveling was proposed by an American physicist named Ron Mallett. It involves one resource that we know for sure is abundant in the universe – light. The scientist proposed a theory about time travel that would use a rotating cylinder of light. He believes that if something was dropped inside this swirling cylinder, it could be moved in both space and time, similar to how a bubble moves when you swirl it with a spoon in your coffee. According to Mallett, the right shape of the cylinder could allow for traveling to both the past and the future. The physicist has been trying to raise money for an experiment to test his theory. This experiment involves dropping tiny particles, called neutrons, through a circular arrangement of spinning lasers. However, other scientists say Mallett's theory is impossible and there's no need to test it further. Well, even if we eventually figured out a way to travel back in the past or to the future, would it be safe? Scientists have been talking about a problem called the paradox of time travel for a long time. The main question is what would happen if you went back in time and did something that changed the future. However, a new study from researchers from the University of Queensland says that this problem might not be real after all. The scientists have done some calculations and found out that even if you had changed something in the past, the timeline would still end up the same way. Another variation of this problem is called the grandfather paradox. Imagine going back in time and preventing your own grandfather from having offspring. Come to think of it, it automatically means you shouldn't exist in the first place. If your grandparents didn't have your parents, how can you exist at all? Well, these days scientists are certain that even if you did experience something like that, you'd still exist in the present. That's because the timeline that already exists has a way of adjusting itself, regardless of where people are in time and what they do. Or somehow get 1.21 gigawatts in a DeLorean and make like Marty McFly.
An ancient painting from the 1860s has a little surprise that will make you giggle. There's this lady walking with her eyes glued to something. Does she have her head buried in a phone? It's hilarious how things haven't changed much, except for the old-timey clothes she's wearing. This discovery went viral when some sharp-eyed visitors spotted it in a museum in Munich. The painting in question is The Expected One by Ferdinand George Waldmuller. Turns out she's not a time-traveling fashionista. She's just lost in the world of hymns and prayers, according to the gallery. Yep, she's engrossed in a good old hymn book, not Facebook. Back in the day, around 1850 or 1860, every single person who laid eyes on this painting would have instantly recognized that she was all caught up in a hymnal or prayer book. But today, let's be real, we compare it to a phone. Now we're about to embark on a journey through time and fashion. In 2011, the internet exploded with excitement over a mind-boggling photo from 1941. What was so special about it, you ask? Well, it showcased a person dressed in a modern-day fashion. They called him the time-traveling hipster. Sleek sunglasses, a cardigan over a sweater, and a hairstyle that screamed, "I've just rolled out of bed." This guy was the epitome of swag, even in the 40s. I mean, he would fit right in the streets of LA today. But here's where Einstein's theory of space and time come into play. Our inability to teleport ourselves across eras keeps us guessing about this mysterious man. The most amazing thing, though, is that his clothes are actually quite fitting for his era, too. Those wraparound sunglasses he sported, they were all the rage in the 1920s. Next, his t-shirt proudly flaunted the logo of the Montreal Maroons, a pro hockey team that graced the ice of the National Hockey League from 1924 to 1938. While this fashion-forward fellow may seem like a time-traveling trendsetter, his style was actually on point for 1941. Now, how about unraveling the secrets of the past with a World Cup moment? Brazil triumphs over Czechoslovakia in the epic 1962 final. But forget about the game for a moment, because there's something even juicier at play. The device in the hands of a photographer. It seems like this photographer is flaunting a flip phone. Obviously, flip phones didn't hit the market until 1996, and they didn't become all the rage until the mid-2000s. It's as if this time traveler is rocking a timepiece from 2007, back when the mighty Motorola Razr ruled the world. If you look closely, you'll see that this device is none other than a good old box camera. You can operate those with one hand, making them a go-to for capturing timeless moments. And if we zoom in on the details, it appears that his camera has a fancy attachment fixed on top. A flashbulb, perhaps? So as much as we'd love to believe in time-traveling paparazzi, it seems like we've stumbled upon a delightful case of mistaken identity. Is it just me, or is this ancient Greek statue showing a laptop with USB ports? So here's the scoop. This statue is called Grave Naskos of an enthroned woman with an attendant, and it's causing quite a stir. Some people are convinced that this ancient artwork is a legit time-traveling laptop. This statue, displayed in the J. Paul Getty Museum in California, was originally used as a funeral marker way back in 100 BCE. It stands a little over 37 inches tall and showcases a woman chilling on a throne-like chair while a young servant holds open a slender box for her inspection. Sounds pretty normal, right? But the internet was buzzing with speculation and wild theories about ancient Greeks with secret laptops. Brace yourselves for the jaw-dropping revelation behind the 800-year-old mobile phone that's been causing a debate. An image surfaced online claiming to show an ancient mobile phone dug up by archaeologists. That ancient tablet was claimed to date back to the 13th century BCE. By that time, the Sumerian writing style had been around for ages. Let's not forget that cuneiform tablets are as common as pigeons in the city. An estimated 2 million of these tablets have been unearthed. The language was a real head-scratcher until the 19th century, when scholars cracked its code. Cuneiform was the writing system developed by the ancient Sumerians way back in 3500 to 3000 BCE. They were the original wordsmiths, paving the way for all the future Shakespeares. This whole story, too, turned out to be a hoax. Babylonokia is actually an artwork from 2012 made by artist Carl Weingartner, who crafted a clay tablet that looked like a time-traveling mobile phone. So it was a modern-day artwork covered with ancient script. But hey, let's keep searching for those hidden secrets of the past. A couple of years ago, archaeologists went digging in Mongolia and stumbled upon an ancient mummy. Experts noticed something peculiar about her footwear. They screamed Adidas trainers. Did this ancient lady have a penchant for sporty kicks? They examined the body and estimated it to be 1,100 years old. It turns out our funky footwear-loving mummy was most likely a Turkic seamstress. Perhaps those shoes were part of her work attire, keeping her stylish while stitching up a storm. She also had a whole treasure trove of ancient goodies with her. We're talking about an ancient clutch bag, a mirror, a comb, and more. There was one thing missing: a cell phone. It seems our time-traveling dreams will have to wait for another day. So my fellow adventurers, while the Adidas-esque footwear raised some eyebrows, it turns out our mummy friend was just a fashionable seamstress strutting her stuff in ancient times. A photo from over 100 years ago features a group of suave Canadians lounging on a scenic hillside. But wait, there's our star attraction, a young man flaunting an outfit straight out of a tropical paradise. Picture this: a snazzy t-shirt, shorts that scream beach vibes, and a head of hair that's definitely seen better days. Who knew time travel came with a dress code? Some say the woman on the right is pointing in disbelief, while others claim everyone's faces are frozen in sheer astonishment. Would a genuine time traveler actually cruise through the ages dressed like a misplaced beach bum? So while we soak up the excitement of this eyebrow-raising enigma, let's remember that fashion choices can be as unpredictable as the time-space continuum. What if we set aside time traveling and took a look at the images of people doing modern things a century ago? Feast your eyes on old snapshots. For example, take a look at these people on a roller coaster. I guess they were into amusement parks too. Now look at this gentleman with his pair of roller skates. Next up, we have photos where people pose with goofy faces. It's nice that it's not just us modern-day people who want to mock each other. Shall we dive into a 1915 photo showing us a deep-sea dive? People just don't wake up one day and decide to dive into the waters. They learned it over time. We didn't invent the group selfie. People have been taking selfies since the early days of photography. Do you think we'll ever be able to invent a time machine one day?
December 4th, 1970. Pilot Bruce Gernon had 2 passengers on board his Beechcraft Bonanza single-engine aircraft, his father and business partner. They took off from Andros Island in the Bahamas and headed northwest for the Florida coast. Sure, they were in the infamous Bermuda Triangle's airspace, but this was a typical flight Bruce had made dozens of times before. The trip usually took about an hour and a half with no hiccups whatsoever. Bruce took off and started gaining altitude. Strange things started happening right from the get-go. At first, he noticed a small cloud up ahead, but it kept growing. Not from the plane getting closer. This thing was actually getting bigger in size. Bruce had to fly through it, and he came out the other end just fine. He gained altitude, and yet another mysterious cloud appeared. This one was massive, and Bruce had no other choice but to fly through it too. At that moment, it got dark as night all around the aircraft. But this wasn't a storm cloud, and it wasn't raining. Bruce was starting to get worried, and then, bam! He saw flashes of white light. Bruce kept flying for another 30 minutes when he realized this was the same cloud he had gone through earlier when he started to climb. But now the cloud was cylindrical, and the plane was flying through its center. It was wide and seemed endless. Bruce thought he could never get out of that trap. But a minute later, he saw light at the end of the tunnel. But all of a sudden, the walls of the cloud tunnel began to narrow. They were closing in on the plane. The navigational instruments started wigging out. The compass was spinning by itself counterclockwise. The walls kept narrowing, smaller and smaller, wrapping like a vortex. The electrical instruments still going haywire. Bruce was running out of time. He had to get out of this place fast. A grueling 20 seconds later, he burst out of this foggy trap. As Bruce described later, he felt weightless for 5 seconds as his plane left the tunnel. The clouds dispersed, and now the aircraft was in a grayish haze. The men let out a big sigh of relief. He immediately grabbed the radio and contacted ground control to determine his location. But when the dispatcher looked at the green screen, his face became contorted with confusion. Bruce's plane wasn't on the radar. It was as if the thing was invisible. But then the dispatcher said the aircraft was already in Miami airspace. Bruce was utterly shocked. It just couldn't be true. Remember, the whole trip usually took around 90 minutes, but this time, it took just 47 minutes to get to the destination. His plane didn't magically gain some supersonic speed beyond the model's limited max cruising speed. This was physically impossible. The dispatcher must have made a mistake. But when the clouds parted, Bruce saw that he really was over Miami. The plane landed safely, and it was time to try and solve this mystery. Bruce checked the remaining fuel and his watch. After a short calculation, he was only more confused. The plane hadn't gone through the amount of fuel it should have. Archive records show that 84 sunspots were recorded that day, as well as a huge solar wind. This would cause disturbances in the Earth's magnetosphere that could throw off the plane's instruments and radars. But so far, no one has been able to explain how the plane got to Miami so fast. Maybe in the future, the truth will be revealed. In the meantime, it remains another mysterious riddle of the Bermuda Triangle.